Welcome to Chapter 23B. The topic is lenses. We're going to describe the types of lenses, the kinds of images that are formed by lenses. And of course, we've done this already. We talked about mirrors, virtual and real images. And we're going to use the lens equation, which, by the way, is pretty much the same as the mirror equation, to relate focal length, radius, distances to object and image, and orientation and type of image. Okay, so remember there are two basic types of images. One is a real image. A real image is the light will actually pass through the real image. If you put a view screen at the image's location, you'll actually see an image forming on the screen. The light rays, of course, then form the image, and real images are typically upside down or inverted. If the image requires a visual system and an observer, it is a virtual image. So, for instance, reflection in a plane mirror is a virtual image. No light actually passes through a virtual image. If you put a view screen at the image's location, no image will form on the screen. And that's because our brains are needed to form the image from the projection or extension of the imaginary light rays. Virtual images are usually right side up. Mirrors and lenses can form both real and virtual images, depending on the location of their focal point and the object. Okay, now all lenses are formed from spherical refracting surfaces. Basically, what a single spherical surface that refracts light can form an image. The object distance is p, the image distance is I, the radius of curvature r of the surface are related by n1 over p plus n2 over I equals n2 minus n1 over r. n1 is the index of refraction of the material where the object is located, and n2 is the index of refraction on the other side of the surface. And here are some spherical surfaces. This is basically the sign convention for this. It does not necessarily refer to these ones down here. So as I mentioned before, real images form on the side of the refracting surfaces opposite of the side that the object is on. Virtual images form on the same side as the object, and of course then as I is negative. Sign convention: when an object faces a convex refracting surface, R is positive. When it faces a concave surface, R is negative. Now, be careful with this. This is the reverse of the mirror sign convention. This follows the lens sign convention, which we'll go into later. Virtually everything about mirrors and lenses are reversed. They use the same equations, as you will find out, but there are many of the same equations, but the sign conventions are reversed. Okay, here's the first example. Here's the object, and here's the spherical refracting surface. As seen by the object, this is a convex surface, so R is greater than 0. Here's medium number 1, of index of refraction n1. Here's n2. Here's the image, of course, inside of n2. Here's the center of curvature. Here's the radius of curvature right here, and R is greater than 0. Okay, here is a situation where you have an object inside of this medium here. This, of course, is n1 and n2, and now it is facing a concave refracting surface, and this will form a real image. Okay, and then R is less than 0. Here's a situation where you have a virtual image. Okay, here is your object. It is facing a convex surface, so R is greater than 0. And the virtual image is forming out here on the same side. Here, of course, you have the object is right here. O is the object. And the image is formed here. It is facing a concave surface. And, of course, this will be a virtual image because it's on the same side as the object. Here, of course, is the object for O, and here is the image, and this is a virtual image, and it's facing a concave surface, so R is negative. Here's the object, here's the image. This is a virtual image, and N1 and N2, and it's facing a convex surface, so this will be R is positive. Okay, so here's an example. A Jurassic mosquito is discovered embedded in a chunk of amber, which has an index of refraction of 1.6. One surface of the amber is spherically convex with a radius of curvature of 3 millimeters. The mosquito's head appears to be on the central axis of that surface. When reviewed along the axis, appears to be buried 5 millimeters into the surface. How deep is it really? Where is the mosquito? The thing you want to do here, first of all, realize it's a spherical refracting surface. Then you want to do some sort of analysis, and you probably want to draw some sort of diagram. The diagram's on the next page. Okay, so because the object is the head and its image are on the same side of the refracting surface, they're going to be inside the surface. The image is virtual. That means I is negative, and we'll write down negative 5 millimeters. The object is taken to be in the medium index refraction n1. We will have n1 equals 1.6 and n2 equals 1 because it's embedded in the medium. The object faces a concave refracting surface. The radius of curvature is negative, so R is negative 3 millimeters. Now be very careful when you do these things. The biggest thing is getting confused as to what you're looking at. Okay, so here's the image. That's what I meant about the diagram we had before. And the object is here. There's this head. The image will form inside of here. Here's the center of curvature, okay, for the surface. Here are your knowns and unknowns. N1 is 1.6. That's the medium that the object is in. N2 is 1. That's the air. R is minus 3 millimeters. That's the radius of curvature. The object is facing a concave surface, so that's negative. I will be negative 5 millimeters, okay, because the image is forming on the same side as the object, so it's going to be negative. And we need to know P. Okay, that's how far into the amber that this mosquito is. The formula is N1 over P plus N2 over I equals N2 minus N1 over R. Okay, so we will want to, of course, take this formula and play with it a little bit. With a little bit of algebra, we want to solve it for P. When we do that, P equals IR N1 over I times the quantity N2 minus N1 minus R N2. At this point, we can start sticking numbers in here. Be very careful with signs. Make sure that your units, okay, just make sure they're all consistent. It turns out when you do all of this, P is 4 millimeters. Now, what does that mean? That means P is inside the amber, 4 millimeters inside the amber. That's where the mosquito's head is located. So that's how far below the surface of the amber that the mosquito's head is. Okay, now thin lenses are made with true refracting surfaces and come in two basic kinds. Converging, which are convex positive lenses, are thicker at the center than at the edges. They converge light, so in other words, when parallel light comes in, it converges to a single point. We're going to call that the focal point. It acts as a magnifying lens. Okay, and this is what the kind of lens, you give a kid a lens, okay, magnifying lens, what's he do with it? He burns ants with it. Now you can see why that is. Here's the sunlight coming in. It brings the light to a sharp focus on the ant. And this acts like a concave mirror. And it can produce real images if the object is beyond the focal point, or virtual ones for objects that's inside the focal point. The other type of basic lens is a diverging concave or negative lens. So it's this one. It is thinner at the center than it is at the edges. It diverges light, so parallel light that comes in has a tendency to diverge. It acts a lot like a convex mirror, and it only produces virtual images. Now there's some key features and things, little landmarks you need. Okay, the central axis, principle of central axis, is a line joining the centers of curvature of the two lens surfaces. In other words, it goes right through the center of the lens. It's pretty much the same as it was for a mirror. The focal point, just like for the mirror, is a point at which, if the light is coming in as parallel, all the light rays will come together at the focal point. The focal length is the distance between the focal point and the actual center of the lens. And notice that lenses have two focal points. That's because the light can come from, if the light's coming from this side, it'll typically focus at this point for this type of lens. If the light is coming, parallel light's coming in from this side, it'll focus at that point, focal point. So lenses have two focal points, and typically they're equidistant from the center. Basically, a mirror, of course, will reflect light, bring it into focus, but a lens will bend or refract light. So mirrors are reflectors, lenses are refractors. Be careful. There's only a two-letter difference between these two words. And when you read questions, test questions, or anything else like that, please make sure that you pay attention to these tiny details. So what a lens does is it bends or refracts light, bringing it into focus. And this is basically how a magnifier works. This is a converging lens, okay? And a magnifier would take the light from an object and produce a large virtual image that your eye can examine in much greater detail. That's why it's called a magnifying lens. Make the image very much bigger than the object. Now, a converging lens can project a real image if the object is located beyond the lens focal point, just like for the concave mirror. And P then will be greater than F. And this, of course, if you are looking at this in a classroom over a projector, and the projector, or you're looking at a movie projector, old-fashioned movie projectors, right? They project a real image of the slide onto the screen. And real images are often upside down. Now, how does a projector get around that? Well, they have a mirror or something like this to turn before it gets here, right in here, they turn it upside down again. Or out here, they turn it upside down. Upside down twice is right side up. Now, there's something called the lens maker equation. For an object in front of a lens, the object distance P and the image distance I are related to the lens focal length, the index of refraction N, and the radii of curvature R1 and R2. Now, R1 and R2 are the radii of curvature of both sides of the lens. We'll explain that later. 1 over P plus 1 over I equals 1 over F. That's the mirror equation. This is the rest for the lens equation. N minus 1, that quantity times this quantity, 1 over R1 minus 1 over R2. Now, R1 is the radius of curvature of the lens of the surface nearer the object. R2 is the one that's further away from the object. So if you look at where the light's coming from, it's going to hit R1 first and then R2. Real images, that is, I is positive, form on the opposite side of the lens from the object. Virtual images, that is, I is negative, form on the same side of the lens as the object. Light passes through a real image, and if you put a screen there, you'd see an image on the screen. The sign convention is R is positive for objects facing a convex surface, and R is negative if the object faces a concave surface. Now, this is the opposite of the mirror convention, so be very careful when you're doing your homework. If the lens is surrounded by some medium other than air, say corn oil or water, with an index of refraction n mead, then we're going to replace this n here with n over n mead, where this is the end of the refracting material, the lens. Now, if you look at this, if n equals n mead, n over n mead is 1, and 1 minus 1 is 0. At this point, this means, of course, over f becomes infinity. Okay, so the lens doesn't focus anything then. This is what happens to you when you swim underwater without goggles on, because the index of refraction of your cornea and your lens is very close to that of water, which makes it very hard to focus. It moves the focal length of your eyeball instead of being the size of your eyeball, so the focus is on the retina where it's supposed to. It'll focus behind your head somewhere. That's why everything looks real fuzzy when you're underwater. Okay, when rays that are parallel to the central axis of a converging positive lens are sent through the lens, they will refract twice, once at the surface, where they encounter the slower medium, and then again as they speed up coming out of the surface. The curvature of the two surfaces causes this bending here. And this double refraction causes the rays to converge and pass through a common focal point, F2, at a distance F from the center of the lens. This is a converging lens, and a real focal point will exist at F2, and the associated focal length is F. And you can reverse this. Okay, lenses have two focal points. You have parallel rays coming in from the right here. They will converge and focus at F1. For a thin lens, these two focal points are equidistant from the lens, so this F is the same as that F. And because this is a real focus, F is positive, and that's the reason a converging lens is also called a positive lens. And like concave mirrors, converging lenses can also produce virtual images. If the object is located between the focal length between F and the lens, within the focal length, then it's going to make a virtual image. We'll show you that later. Okay, now the other type of basic lens is a diverging or negative lens, and you can see why this is in a minute. So you have rays parallel to the central axis, and they are sent through the lens. They will refract twice. Here's a close-up of this, and here's one refracting surface, and here's the other one. Okay, so they bend twice, and the shape of these two surfaces causes this type of bending. This double refraction will cause the rays to diverge, and they never pass through a common point. That's why it's called a diverging lens. But you can extend the emerging rays back to a common focal point right here. And that focal point is the distance F from the center of the lens. So the lens has a virtual focal point at F2. If instead you sent the rays through in the opposite direction, just flip this diagram around. You're going to find out that the extensions go through this focal point. This will be symmetrically placed on either side if the lens is thin, and in this class, the lens is thin. Because the focal points of a diverging lens are virtual, the focal length is negative. So a diverging lens is also called a negative lens. Like convex mirrors, diverging lenses only produce virtual images. As we did in mirrors, we can do ray tracing. We have three special rays. This is for a real image. And for instance, a ray that is initially parallel to the central axis of the lens will pass through the focal point. Any ray that's parallel to the central axis goes through a focal point. A ray that initially passes through a focal point, guess what? It's reversible, so it will emerge from the lens parallel to the central axis. So any ray that goes through a focal point will emerge parallel to the central axis. That's ray 2. Any ray that goes through the center of the lens will not change direction at all, because these two surfaces here are almost exactly parallel, so it's just going to go straight through. Now, what we need, in order we need to do this, we typically draw an object represented by an arrow. We put the butt of the object along the central axis, because then we know that this image somewhere, that butt's going to locate it along the central axis. Then we, of course, we use the tip of the arrow to represent the size of the object, and we draw the rays from the tip using these rules. And where the rays intersect forms the tip of the image. And the object, or the image is located between this butt and that tip. So that locates the image and tells us its size and its orientation if you use the arrow. That's the reason we use an arrow. Virtual images, just like we did with mirrors, require a little bit of extra effort called ray extensions. And there are 3 special rays, and these are basically the one we had before, the one that's parallel, the one that goes through the focal point, and the one that goes straight through the center of the lens. So in the previous thing, we would modify ray 2. Here's the object, and we're going to take an extension that goes through the focal point through the tip of the object, hits the lens, and comes out parallel. Here's another ray here from the parallel to the central axis, hits the lens, goes through the focal point. So that is ray 1 and ray 2. And of course, we also have this ray here that goes through from the object through the center of the lens, and the extension would go backwards to this. Now, we put the butt of the object on the central axis. That means the butt of the image will also be on the central axis. And any 2 of these rays here will determine the tip of the image. Okay, any 2 of these rays coming from the object's tip will determine the tip on the image. And this, of course, is pretty much the same thing here. We have a parallel ray. Its extension is going to go through the focal point. Here we have one that would go through this focal point here on this side, comes out parallel. And here we have one that goes right through the center of the lens. And by drawing these rays here and looking for any 2 that cross, gives us the tip of the image. And of course, the butt of the image is on the central axis. Okay, a praying mantis and a thin lens. A praying mantis preys along the central axis of a thin symmetric lens 20 centimeters from the lens. The lateral magnification of the mantis provided by the lens is m equals minus 0.25. The index of refraction of the lens material is 1.65. Determine the type of image produced by the lens, the type of lens, whether the object, the mantis, is inside or outside the focal point, on which side of the lens the image appears, and whether the image is inverted. And what are the 2 radii of curvature of the lens? Now, the physics of this is, of course, thin lenses and refracting surfaces. It's kind of a long problem. Okay, so the first thing you want to do is write down the knowns and unknowns, paying particular attention to the signs, because the sign conventions were the devils in this detail. Okay, m is minus 0.25. N is 1.65, P is 20 centimeters, the type of the image, type of lens, location of object, image orientation, and R. Okay, at this point, you start looking for formulas. M equals minus I over P. 1 over P plus 1 over I equals 1 over F equals N minus 1 times the quantity 1 over R1 minus 1 over R2. Now, the lens is in error, so we can use a simplified version of this. This will be the index of refraction of the lens material itself. The algebraic solution of M equals minus I over P, and I will be minus MP, and watch your sign. Be very careful with this. It ends up being 0.25P. Since P is greater than 0, I is greater than 0. If it's greater than 0, it's a real image. Now, check with that. They said that this means that there's a converging lens here, and the object is located outside the focal point. Now, because it is real, and it's only one lens, the image is going to be inverted, and it'll be on the side of the lens opposite the object. And this is confirmed by the negative sign on M, and also confirmed by this drawing here, of course, which we drew that the object's outside the focal point, and you can see you trace your rays, and there's your image, and it's upside down. Okay, so the lens is symmetric. So R1 for the surface near the object, that's the surface, and R2 for the surface away from the object will have the same magnitude, R. We're just going to call it R. The lens is a converging lens, so the object will face a convex surface on the nearest side. So this surface is convex as the object sees it, and that means it's positive. Similarly, it faces a concave surface on this side. Remember, this is the object, and you're looking at this surface here. So R2 is negative R. And we can relate these radii of curvature to the focal length via the lens maker's equation. And that's the only equation we have for this. We can relate F to the object distance and image distance via the thin lens equation. So we're going to write down the knowns again, just to repeat them and to make sure we've got them correct. Watch your signs on everything, watch your units. Okay, we have 1 over P plus 1 over I equals 1 over F. That has to equal N minus 1 times the quantity 1 over R1 minus 1 over R2. And we can start plugging some numbers in to make this a little easier. and work on, get this down here. We can condense this a little bit and make this 1.25 over 0.25p. And we can put in our values, 1 over r for 1 over r1 and minus a 1 over minus r, remember that, for 1 over r2. And we can condense this side. We can do a little bit more algebra on it, and we will find that r equals 2p times n minus 1 over 5. At this point, we're pretty much ready to plug numbers in. We watch our units, r times 2 times 20 centimeters times 1.65 minus 1 divided by 5. R is going to come out to be 5.2 centimeters. Now, at this point, we should go back and plug it into the other formula, 1 over p plus 1 over I equals 1 over f. And we can say that f equals the inverse of p to the negative inverse of p plus the inverse of I. Plug in I, of course, is 0.25p. And now we can plug our numbers in. And we can say for 20 centimeters for p, take the inverse of that. And of course, this is 0.25 times 20 centimeters. And don't forget this. This is where people screw up. It's sort of like that. If you look at this equation, does this remind you of something? Remember two parallel resistors? And remember resistors in parallel or capacitors in series? 1 over R1 plus 1 over R2 equals 1 over R equivalent. Remember I told you could make that product over sum? Okay, so you've already done this equation, so you can reuse that if you use symbols. Okay, so the focal length ends up being 4 centimeters. The object is outside the focal length. P is 20, so it's greater than this. So the picture is correct, and this is a real image. It is inverted and smaller in size than the object. It's 1/4 of the linear size of the object. Now, we can, if we have multiple lenses, what do you do if you have multiple lenses? A lot of things like cameras and binoculars and telescopes have multiple lenses. In fact, telescopes have lenses and mirrors. How do you handle things like this when you have multiple lenses? Well, the best way to do this is to chunkify, break it up into little pieces. You do one lens, okay, do the one that's closest to the lens that the light goes through first, okay? So the first lens is the lens that is closest to the object. Do that one, ignore everything else. Find out where the image forms in the first lens. The image from the first lens becomes the object of the second one. You have to be careful to get the distances correct, because now you're referring to the second lens. And then the secondly, you ignore the first lens, do the second lens, and find out where the image from that one is. So you can use thin lens equations or ray tracing to find the distance between the lens 1 and image I1. So you find this in here using O and P and the lens equation or ray tracing. And of course, P1 will be this distance here for the object from lens 1. Then you ignore lens 1, but you have to notice, okay, you have to figure out what this distance is. So you figure out, use this, okay, and this right here, the distance between the lenses, to figure out what this is. Be very careful with your signs. Remember what you're doing here. You are interested in this distance between this image, which is the object for the second lens, and the second lens. That will become the new P. Now, sometimes this can be negative. It can be on the other side. We'll show you something like that. Then you use the lens maker's thin lens equation, ray tracing, whatever you have, to figure out where the final image is. Now, if there's a third lens, okay, this would be the object for the third lens. Say the third lens might be out here. Again, be very careful with your signs. O3, you can have third lens here. If the third lens is here, then P3 is going to be negative. Repeat step 2 to find the distance to the image 3 and keep on going. Repeat this for as many lenses as you have. You can also do this for a mirror, substitute for a lens, but be sure to use sign conventions for mirrors and be careful of distances and signs. So here's some examples of this. Look carefully here. And here is the second lens. That's where the second lens will be. This is the first lens right here. Here's your object. Here's the focal length of the lens. The object is outside the focal length. It's going to be a real image. It's going to form over here. This real image will become the object for this lens, and that's down here. So again, here's the second lens. Here's the focal point of the second lens. And now we have to figure out this distance. And that will be P2. And this will be a real image, okay, because this is outside of the focal length of lens 2, this one right here. So this distance is greater than that. And this will be a real image. And because this is upside down, the real image will be flipped. So this will be right side up in the final run. And this will be the final image, somewhere out here somewhere. Now we have the same thing here. Of course, the object is outside the focal length, so it's going to make a real image will be upside down. But now our second lens is inside, is here. Okay, it's on this side. And so what happens then is now this is the object for the second lens. Notice that it's on the other side. So this means P2 is negative. So be very careful with this. And then it's going to form a virtual image, which will have the same orientation as this. So it's going to be still upside down. So P2 can be negative. If that's true, be very, very careful with the sign. Please don't do this when you're tired, because I've done that before and chased the negative sign all over the place. Another example here, we have the object is outside the focal length. Here's the focal length. Here's where the lens is going to be, the other lens. Here's the image from this lens. That's I1. Now we draw this here, okay? And here we have this object, which is the old image, I1, is now inside the focal length of the lens. So it's going to be a virtual image. It's going to be over here. It's going to have the same orientation. It's going to be on the same side, on the same left side of this lens. Notice the P2 is inside lens 2's focal point. That's the reason it's making a virtual image. And because this image was upside down and the virtual image has the same orientation as the object, which is now this image, which was this image, it'll be upside down too. Now we've got the object inside the focal point of this lens. And that means it's going to make a virtual image over here someplace on the same side as the object. It's going to be right side up. The new lens is over here. So we ignore this stuff here. And now we have a new object for this lens. So this is O2. And that's going to be way outside the focal point. So it's going to make a real image on this side. And the real image will be upside down. And it'll show up to the right of lens 2. Okay, so that was for convex lenses. How about for a concave lens? For the first lens. Okay, concave lenses do nothing but make virtual images. So if it's the first one, first of all, I know it's going to be upright. It doesn't matter where it's going to be over here. It's always going to be on this side. If this object's anywhere on this side, the image is going to be here and it's going to be right side up. Now we put a new lens in here. So this image now becomes the object for this new lens. And here's the focal point of new lens. And notice that it is beyond the focal point. So it is going to be a real image. It's going to be upside down somewhere over on here side, right side. Okay, here we have another situation. We have a convex lens. We're outside the focal point. We know that creates a real image on this side of this lens, opposite the object. We have a new concave lens over here. Here's the image for the concave lens, and concave lenses do nothing but create virtual images. So the orientation will be upside down like this one was, and it is a virtual image because that's the only thing concave lenses can produce. And by the way, this is one of the only ways you can get a upside down image out of a concave lens. You have to have another lens to make that work, or a mirror. Okay, so we have two lenses in one seat, a jalapeno seat. And it is placed over here in front of two thin symmetrical coaxial lenses. Coaxial means they're on the same axis. Focal length of F1 is positive 24 centimeters and F2 is positive 9 centimeters, respectively, and with the lens separation between these two lenses of 10 centimeters. The seed is, that's the distance to the object, 6 centimeters from lens 1. Where does the system of two lenses produce an image of the seed? So the physics of this is a system of two thin lenses, and the worst thing about this, and I always write this down, sign conventions. Okay, make sure, because this is where you really get confused. Draw a diagram, be very careful with your signs. Okay, the first thing we do is we pretend this lens is not even here. We ignore it. We analyze the first lens. And the image produced by lens 1 becomes the object seen by lens 2, and then we have to, of course, figure out what P2 is. Then we analyze lens 2, paying special attention to sign issues. P2 might be negative. Make sure we actually get the correct distance. And then we use that to find the final image I2 produced by that lens. Okay, we write down everything we know. We know that F1 is positive 24 centimeters. It's a converging lens. F2 is also positive 9 centimeters. It's a converging lens. We know the distance between the lenses is 10 centimeters. We define that as L. Here's our diagram. And notice that the object is inside the focal length. So this means I1 is a virtual image. So it's going to be on this side of the lens, on the left side of the lens, and it will have the same orientation, so it's going to be upright. same rotation as the seed. Okay, now once we do that, then the image of lens 1, okay, so this is lens 1 by itself. Here is lens 2's object, okay, the same point. Now we had to be careful to define P2 correctly because we have an additional complication of this here plus that. So actually P2 will be I1 plus L. Apply to lens equations, and we notice that it's probably going to be outside the focal length of this lens. This is going to be a real image, and it's going to be upside down. Well, we'll see. Okay, the formula is 1 over P plus 1 over I equals 1 over F. And we also have to remember that P2 is L plus the magnitude of I1. Now, so we write everything in here. Solve this. I1 equals F1 P1 over P1 minus F1. I2 equals F2 P2 over P2 minus F2. Now we can start putting the numbers in. Be careful with the units. Make sure the units are all the same so you come up with something that makes sense. And when you do this, putting in your F1 of 24 centimeters, your P1 of 6 centimeters, P1, of course, F1. Be careful with the negative sign here. I1 is minus 8 centimeters. Now, that means it's a virtual image, and we probably did the diagram correct. So I1 is forming 8 centimeters to the left of the center of lens 1. Now, that we have to use that to determine where, relative to lens 2, the new object, that is the image from the first lens, is. And of course, we had to add L, which is at 10 centimeters, to this 8 centimeters here. So P2 is 18 centimeters. I2 would be F2 P2 or P2 minus F2, and we plug in our numbers here, being careful with everything. And we notice that I2 is 18 centimeters, and it's going to be over here. It'll be a real image. It's positive, will be inverted, and located 18 centimeters to the right of lens 2. Okay, now aberrations are distortions of an image. And mirrors can suffer from spherical aberration, but not chromatic aberration. Spherical aberration is a result of light passing through the edges of a lens or reflecting from the edges of a mirror and focusing at different points from where the light from the center of the lens or mirrors comes from. So basically what happens here is the light coming from here has a focal point here. The light coming from here has a focal point out there. And you don't get a sharp focal point, you get a blurred image. Chromatic aberration is a result of various colors having different indexes of refractions in the material, different speeds in the material. Typically, the short wavelengths are refracted more than the long wavelengths. So typically what happens is the focal length of the blue light is smaller than the focal length of the red light. Now, astigmatism occurs when the front surface of the eyeball or cornea is unevenly curved, and that ends up giving you blurry vision. So it's sort of like if this didn't have a nice spherical refracting surface, maybe it's got some dings in it and gouges, and it's not a nice smooth surface. Now, spherical and plane mirrors and thin lenses, this is a sign, convention, and formula recap, and you might want to put this somewhere in your notes because it can be kind of useful, or come up with your own, that's even better. Here's the formula. 1 over P plus 1 over I equals 1 over F. The magnification is H prime over H. Okay, H prime, of course, the height of the image, and H is the height of the object. And magnification is also minus I over P. Okay, I is the distance to the image, and P is the distance to the object, and F is the focal length. If the M is positive, the image is upright, has the same vertical orientation of the object, and probably the image is virtual. Probably. If the image is negative, the image is inverted, oriented opposite to the object. For a spherical mirror, F equals R over 2. For a plane mirror, F is infinity. The mirror is positive for P, I, and F on the front of the mirror. That's the side the light comes from. And the image will be real inverted for I positive. That's the front side. That's the side the light comes from. It is negative for P, I, and F on the black side of the mirror. And the image will be virtual and upright for negative I. F and R are positive for concave mirrors, and F and R are negative for convex mirrors. For a thin lens, we have 1 over F equals N lens divided by N surface minus 1, that quantity, times 1 over R1 minus 1 over R2, that equals 1 over P plus 1 over I. For a lens, F is positive for a converging or convex or positive lens. A converging lens is thicker in the center than at the edges, and like a concave mirror, can produce either real images for P greater than F or virtual images for P less than F. F is negative for diverging, concave, or negative lenses. A diverging lens is thinner in the center than at the edges. Diverging lenses only produce virtual image, just like a convex mirror. P is positive for an object in front of the lens. Front is on the same side the light comes from. P is negative for the object behind the lens. and this happens for systems of more than one lens. I is positive for the image behind the lens, and you'll get a real and inverted image. So assuming it's just one lens. It will be behind, that is the side the light does not come from. I is negative for an image in front of the lens, and it will be a virtual and upright image for one lens system. The front will be the same side as the light comes from. R1 and R2 are positive for convex surfaces as seen by the object. R1 and R2 are negative for a concave surface as seen by the object. And you're welcome. You should write this stuff down someplace. Take it with you on test. Do it early so you get the advantage of it while you're doing your homework. And then if you're making mistakes in your homework, you can make it better. Now, there's some useful variations on the lens mirror formula. This is the original equation. You can do some minor algebra on these. You come up with some very useful versions of formulas for M and I. M equals F divided by the quantity F minus P. I equals PF divided by the quantity of P minus F, and also equals P times M. Now, these are not easy to remember, but I don't want you memorizing this stuff anyway, so you might prefer these. And you're free to handwrite them down, bring them on your cheat sheet with you on test. Now, which one of the following statements best explains why chromatic aberration occurs in lenses, but not in mirrors? Well, the main thing about it is that mirrors are reflectors and lenses are refractors. Chromatic aberration only occurs when light is being bent, because different colors of light are refracted by different amounts as the light passes through the lens, because the refractive index will vary with the wavelength of the light, or the color of the light. Okay, now parallel rays of red light that are directed at a converging lens are focused at a point P on the central axis to the right of the lens when the lens is surrounded by air. If the lens is surrounded by water instead of air, where will the red parallel rays be focused relative to point P? Well, air has an index of refraction of 1. Water has an index of refraction of 1.33. And if this is air, this is going to be a certain number. Okay, the lens is surrounded by air. If it's water, this is to be greater than 1. So this will be smaller than it was before. If this is smaller, this is going to also be smaller, and F will be larger. So when you put this in water, focal point is going to be way out over here somewhere. And this is why it's so hard to look at things underwater. So this is basically what I said. Okay, when the lens is surrounded by water instead of air, the ratio N lens over N surrounded is smaller, which makes 1 over S smaller, and F larger, so F moves out to the right. Now, this is basically the same question. The only difference in this question than the other one is that you're using blue light instead. It'll still be further out to this side, okay, but just probably not quite as far, because blue light will have a tendency to focus closer than red light will. Blue light gets bent more than red for most materials. So it's basically the same question as before. It'll still end up being to the right of point P. An object is placed at its distance 2f to the left of a converging lens with a focal length f. Using the thin lens equation, the magnification equation, determine the location and magnification of the image formed by this configuration. Okay, the image will be formed at a distance 2f to the right of the lens, and it has a magnification of -1. Use your thin lens equation, 1 over f equals 1 over p plus 1 over I, as m equals minus I over p. And we can, this is one of those handy little versions of this, m equals f divided by f minus p, or here's another one, I equals pf divided by the quantity p minus f. And of course, p is 2f, so this 2f times f, that's not a typo. I know it looks like one, I always think it is 2 when I go through this slide. And of course, p is 2f minus f. It ends up being 2f. It's positive, this means the image is real, inverted, and forms on the opposite side of the lens as the object, and will be minus I over p, that's minus 2f over 2f, or -1. It'll be the same size, it'll be upside down. And we can check that. M equals f divided by f minus 2f, it ends up being -1. Always check these things if you can. A physics student desires to create a beam of light that consists of parallel rays. Which of the following arrangements would allow her to accomplish this task? Well, if you got a beam of light that consists of parallel rays, you have to make sure that it's a real image, because light does not go through a virtual image. It has to be either a concave mirror or a convex lens. So what you're looking for is concave mirrors and converging lenses. And you want something at the focal point, because if you have light that's coming out parallel, that means the object is located at the focal point. So the correct answer to this is either A or C, a light bulb placed at the focal point of a concave mirror, a light bulb placed at the focal point of a converging lens, a convex lens, positive mirror, positive lens. An object is placed at a distance of 5 centimeters to the left of a converging lens with a focal length of 2.5 centimeters. Using the thin lens equation, the magnification equation, determine the location and magnification of the image formed by this configuration. The image is formed 5 centimeters to the right of the lens and has a magnification of -1. Use your thin lens equation, use your magnification equation. Solve it for M, like we did before. Solve this for I, like we did before. Plug in the numbers, being careful with the units. I'm sorry this wrapped over this other page. But it's I equals PF divided by the quantity P minus F. And ends up being positive 5 centimeters. It's positive, the image is to the right of the lens, that's the opposite side of the object, and it's real and inverted. And magnification is minus I over P, ends up being -1. And we can check this and end up being the same, so the image is inverted, real, and the same linear size as the object, just upside down. An object is placed at a distance 5 centimeters to the left of a diverging lens with a focal length of 2.5 centimeters. Using the thin lens equation and the magnification equation, determine the location and magnification of the image formed by this configuration. And what should be the sign on the focal length? Well, it's a diverging lens. The focal length should be negative. And a diverging lens can only form a virtual image. So if the object is to the left, the image is also going to be to the left. So anything it says to the right is going to be incorrect. So it's negative, and the image is formed 1.7 centimeters to the left of the lens and has a magnification of 1/3. So we use the formulas like we did before, solve them, okay, and we find that I equals PF divided by the quantity P minus F. Plug in our numbers, being careful with the signs on this, and we end up being, okay, be careful when you're doing a minus and negative, be careful with that. Ends up being minus 1.66 centimeters. And this means the image is, like we guessed, to the left of the lens, same side as the object's on, what we call the light side of the lens. And the image is virtual and upright. M will be minus I over P. And I'm sorry, this wrapped around here. So it's minus 1.66 centimeters divided by 5 centimeters. Positive 0.333. So the image is 1/3 of the size of the object, upright and virtual. And we can plug this in here and check and make sure we got the same thing. If you do, you probably got it right. Or maybe you made 2 mistakes. A diverging lens creates what kind of images? Well, it will only create a virtual and upright image. It cannot do anything else. It's like a convex mirror. A converging lens creates what kind of images? Well, converging lenses are positive. They're like concave mirrors. They can make a virtual and upright or a real inverted. So virtual and upright are real and inverted. When parallel rays of red light are directed into a converging lens, they will focus at a point P to the right of the lens. If the red light is replaced by violet light, where will the rays focus? Hint, remember that the index of refraction typically is greater for short wavelengths. So typically, if you have red light, that's going to focus further out than violet light will. And it's going to still focus along the line, the central axis. So they said the parallel rays are directed at what focus point at the right of the lens. If you replace it from a violet light, it'll be shorter focal length. So it's going to be to the left of point P, slightly to the left of point P. And you can see this. Violet light has a slightly higher index of refraction. So that makes this bigger. That makes this lens, this ratio larger. It makes 1 over F slightly larger and F slightly smaller. So it's going to focus closer to the lens because the light bends more for violet light. A thin convex lens is analogous in the way that it handles parallel incoming light to which kind of mirror? Okay, well, it's a convex lens. It's a positive lens. It's going to act like a positive mirror, which is a concave spherical mirror. Thank you very much.